Okay, welcome everyone. Good morning. Let's give a couple of more minutes so that more people can tune in and then we can start. Okay, so it's 2 minutes past 9. Let's start. I think more people can join in as it progresses. Let me do it full screen. Yeah, it works. Okay, then good morning. So this is the third lecture because our lectures are scheduled in 2 hour time slots. So we have 250 hours, 50-minute lectures already done. And this is the third lecture, which we will be covering the switching concept. So it's module 2 or chapter 2 in your switching, routing, and wireless essentials course that's there on Netcad. I hope the Netcad issues with everyone are resolved. If they are still persistent, please email me as soon as possible because Netcad is quite good and resourceful. You would want to check all the contents that are there. So please let me know by mail that if you have any issues accessing the Netcad. There was some troubles with respect to forget password. I think it should have been resolved by now. But if it hasn't, please try to resolve that. And if it is still not resolved, please mail me. Okay, so the module objective or the chapter objective for this one is to explain how layer 2 switch forwards the data. Layer 2 is essentially the layer 2 in OSI model, which is the data link layer. The data that comes in layer 2 is in the form of packets. You might have already studied this in your first year course. So we'll divide this content into two subtopics. One would be frame forwarding, in which we will explain how the frames are forwarded in a switched network. And then secondly, we will discuss about switching domain. We'll see what collision domains are, and then we will compare collision domain to a broadcast domain. So that's essentially the whole crux of it, what we are going to learn in this. Okay, let's start. So the very first point is frame forwarding. As I've already mentioned, the switch at layer 2 of OSI model, which is the data link layer, it has what we call a frame, right? So how does this switching and networking work? We know that the switches can be of many types. They can be layer 2 switches, which work on layer 2. There are layer 3 switches, which could be comparable to the router, but they work at layer 3 essentially of the OSI model. At layer 1, we have hubs. So essentially what hub does is it just floods all the data out of the network. It doesn't do the filtering. It doesn't do the forwarding of traffic. If we compare that to a layer 2 switch, so layer 2 switch essentially performs three types of functions. One, it can flood the traffic. If it's a broadcast address, then it can flood the traffic to all the ports, except for the one that it receives the data from. We'll discuss about that in a minute. And then secondly, it forwards the traffic. So if the destination address, or if you specify to which port or which destination MAC address you want to send the data, it would send the data to that address. So it will forward your traffic in the network. Third thing is that it will filter the traffic as well. So it will see the port numbers, and if your source address is coming from a specific port, it would not send the data to that port from that source address. So it does what we call like filtering of the traffic as well. So it performs these three functions. Whereas if we check out layer 3 router, essentially not a layer 3 switch, but a layer 3 router, it can also do all these functions except for the flooding part. So it can forward the data. If the destination is its in routing address, it will forward essentially the data to that address, right? It can filter if the destination is not in the table, then it can suggest that, okay, I'm not going to take this data because the destination address is not in my table. We'll check about that as well in a minute. And then third thing, which is very important, it would never flood the traffic. So that basically saves you from your collisions as well as your flooding of the network because of unnecessary frame forwardings or packet forwardings. So that's essentially the difference between layer 2 switch and a layer 3 router. So as we know that the switching works on layer 2 of the OSI model, which essentially takes frame as an input. So frames that are coming to a specific port, they are called ingress ports. So if a frame is entering an interface by a particular port, say if in this example, if it is coming to port number 1, the port number 1 would be the ingress port. It have addresses, MAC addresses. So these are just for the sake of showing actual MAC addresses of more number of bits. So there are two terminologies that you need to be comfortable with when talking about switching in network. One's the ingress ports, where the data is coming towards this, to the switch, and one is the egress port, in which the data is exiting from an interface. So you can consider a physical switch having, say, 18 ports or 48 ports, whatever, right? So if we connect one cable to one port, and if the data is coming from that cable and through that port, so that will be the ingress port for the switch, right? And if it is the switch now forwards the data to, say, some other port, some third or fourth port, or some or it will forward the packet to all the other ports, then those will be the egress ports because the data is exiting out of that interface. So the switch forwards based on egress interface and the destination MAC address. For example, let's see if the incoming data is coming on port 1, which has the MAC address of EE. And if it says that the data is destined for EA, right? EA MAC address, because in frame you have source MAC address, you have destination MAC address. So if the data is outbound for EA, it will check from the port table like which port is EA associated with. Now it checks that it associates it with port 4, then it would not forward the data to all the ports, but it would forward the data to port 4. That's how the ingressing and egressing works. So switch uses its MAC table to make the forwarding decision. This is very important. So MAC address table, we will also go about that in a minute, how it is populated, how it checks, and what is it used for. Important point to note in here is that a switch will never allow traffic to be forwarded out of the interface that it received. So for example, if the data was received at interface or port 1, it will never forward the data to the same port, right? Uh, uh, if you talk about frame header, you will have studied in CE 155 as well. Like the structure of the frame, it contains source address, it contains destination address. So source address is used to build, or the destination address as well is used to build this MAC address table. We'll essentially be learning about that. Okay. So if we talk about the switch address MAC table, initially it's empty when you turn on a switch and it has no devices connected to it, it's empty. And it uses destination MAC address to determine the egress interface. Uh, so essentially whatever port is the data coming from and whatever the source address or source MAC address is associated with that, it will put that in its MAC address table. And if the frame would have a destination MAC address, right? And this is also used to populate the MAC address table. I'll show you in a video. But again, as I was saying, so when we switch on a new switch, when we put it or we turn it on, everything is empty. Its MAC address table is empty. And when you connect devices to it, when the devices starts to send the data from that switch, then this MAC address table starts to populate, right? So before a switch can make this decision, or what decision we are talking about, we're talking about where to send the data frame to. It must learn what interface the destination is located. A switch builds MAC address table as it is stored in a very fast memory, which we call as content addressable memory. This is very fast. It does computations in, say, microseconds and milliseconds of time frames. So this is also called MAC or CAM table rather than MAC address table. Mostly we'll use the terminology called MAC address table, but if you are reviewing some literature or studying from some other material as well, you might as well see some of the terms related to CAM table. So CAM table is essentially same. Right, so CAM is a special memory which is used in high-speed searching applications. As MAC address tables or decisions needs to be very fast, so we store these MAC address tables into this memory called CAM memory. So how does it learn? This is essentially the basic step of populating the MAC address table. So switch uses what we call like learn and forward method. So first, it has two steps, step 1 and 2. In the very first step, it would learn, and in the second step, it would forward. So to learn, it examines the source address. Because your data would be coming to a specific port using some cable or device, and it would have source address associated with it. It uses these two things to learn about the source or to populate the source MAC addresses. So it adds the source MAC address if it is already not in the table, as I was suggesting. So if we just turn on a switch, it would not have anything. So it will add the MAC address in the table. But if the switch has been turned on for quite some time, if there has been data frames going in and out of the switch, then it would have its somewhat populated MAC address table. Then it relearns. So if a source MAC address is coming from a specific port, this resets the timer in the MAC address table back to 5 minutes, and it refreshes itself, say, in the time durations of 5-minute intervals. So once we have a fresh source MAC address, if it is again in the list, the timer will be reset to 5 minutes, so that we know that whatever MAC address table is populated, it is the latest one, right? So this is how it learns. In step 2, to examine how it forwards, it again depends upon the destination addresses. So if the destination MAC address is in the switch MAC address table, it will forward out to that very specific port number, right? If it is not in the table, what would it do? It would flood out the data frame to all the interfaces except from the source MAC address, right? There's a very nice video on Netcad which will cover like how switch builds its MAC address tables and how it takes forwarding decisions. So let me start that video for you. I think, let me turn. I hope the volume is all right.
In this video, PCA is going to send an Ethernet frame to PCB, and PCB is going to send an Ethernet frame to PCA. We're going to examine how switches S1 and S2 build their MAC address tables, and also how they forward frames based on the information in those MAC address tables. PCA has an Ethernet frame to send to PCB. The source MAC address of the frame is 000A, and the destination MAC address is 000B. The Ethernet frame is sent to switch S1. S1 receives the Ethernet frame, examines the source MAC address, and notices that this MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that this MAC address is not in its table, so it floods it out all ports. PCB receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices that that is a match and receives the rest of the frame. The Ethernet frame continues to be forwarded to switch S2. Switch S2 examines the source MAC address of the frame and notices it is not in its MAC address table, so it adds the MAC address and the incoming port to its MAC address table. Next, switch S2 examines the destination MAC address, notices that is not in its MAC address table, so it floods it out all ports. PCC receives the Ethernet frame, and its MAC address does not match the destination MAC address of the Ethernet frame, so it does not accept the rest of the frame. The router receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notice it is not a match, so it does not receive the rest of the frame. Now let's have PCB sending a frame back to PCA. The source MAC address of the frame is 000B, and the destination MAC address is 000A. PCB sends it to switch S1. S1 notices that the source MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that MAC address is in its MAC address table, so it sends it out just port 1. PCA receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices it is a match, so it receives the rest of the frame.
Okay, so that was that. Let's go back to the PowerPoint. So one of the questions that has been put in the question and answer is that can we have more than one device connected to a switch's interface? So if by interface you mean, or you're referring to this video, it was the port, right? So you can only have one cable put into that port. So if it is your end device, you'll only have one device. But if you would have your switches or wireless media cables or routers as well, so if you have those intermediary devices, that could be used to have more number of devices to send the data to the same port, not essentially have physical connection to that port, but send the data to the same port. Okay, I hope that answers. So this video was quite good to see how the MAC address tables were built and how they are used to forward the frames, right? Now let's consider the switching forwarding methods. There are essentially two methods. So switches use software on, say, application-specific integrated circuits known as ASICs to make very quick decisions. It will use either of the two methods as shown in the slide. So the very first method is named as store and forward, and then the second one is the cut-through switching. So as the name specifies, store and forward, what do you think it would do, right? It would first store all the details of the packet, the complete frame, and then would forward. And in the cut through, it cuts the chase and it just starts sending the frame as soon as it receives the destination MAC address. So the store and forward switching receives the entire frame. Yes, we just discussed that, and ensures that the frame is valid. And what do you mean by the valid frame? It means that it should pass all the necessary checks. So those checks are performed by 2-3 methods. So one of the very common one is the FCS. So if you have learned about the Ethernet frame, and in the video as well, we saw that there were 4 or 5 bits to it. One was source MAC address. Okay, so that was that. Let's go back to the PowerPoint. So one of the questions that has been put in the question and answer is that can we have more than one device connected used to forward, make very quick decisions? It will use either of the two methods as shown in the slide. So the very first method is named as store and forward, and then the second one is the cut-through switching. So as the name specifies, store and forward, what do you think it would do, right? It would first store all the details of the packet, the complete frame, and then would forward. And in the cut through, it cuts the chase and it just starts sending the frame as soon as it receives the destination MAC address. So the store and forward switching receives the entire frame. Yes, we just discussed that, and ensures that the frame is valid. And what do you mean by the valid frame? It means that it should pass all the necessary checks. So those checks are performed by 2-3 methods. So one of the very common one is the FCS. So if you have learned about the Ethernet frame, and in the video as well, we saw that there were 4 or 5 bits to it. One was source MAC address, one was destination MAC address, and the end one was FCS. So that FCS is the frame check sequence, and it checks for associated errors. Essentially, what it does is it calculates the CRC, what we call cyclic redundancy checks. Cyclic redundancy checks are basically like, you know, matching what the user is saying and what your computation device is saying. So it will essentially check for the size of frame, for example. So it will do its computation. It will have one CRC value for the frame size, and then it will check whether the source address is saying the same, that I'm sending say 512 bits of packet size. So it does this sorts of checks, and if they are different, then what it does is it discards the packet, and if they are not different, we consider that as valid, and then it stores the packet and forwards it using the MAC address table that we just learned. uh, One more thing to note in here is that store and forward will also eliminate runts and giants. How does it do that? We'll discuss as we move along. So as I was saying, store and forward switching does error checking and buffering. So it has two primary characteristics. In error checking, as we discussed, that it checks for frame check sequence for CRC errors. If the CRC errors, or if the size of the frame, say for example, not match, the frames are considered as bad frames and they are discarded. If the FCS sequence is matching, then the frames are forwarded. Second is that it buffers. Buffer has a very good benefit associated with it. It is used to also have port speed. So different ports might have different speed. Say one port is having fast speed and the other one is having slow speed. So buffering allows you to have that sort of adjustment for the potential differences in speed of ingress and egress ports, right? This is sort of the frame header. It has these things: preamble, destination MAC, source MAC, and then type. Then this is part of the frame, and then the end part is FCS. So this is the 4-bit information that essentially is checked in store and forward switching. If we talk about cut through switching, what it does, it will, so in the store